Right now, two planets you will never visit are deciding whether your descendants live in a warm world or under a wall of ice. They've been doing it for millions of years. They're doing it today. And almost nobody on Earth knows their names are even involved. The strangest part isn't that it's happening, it's how quietly. There's no headline, no flash in the sky, no single night you could mark on a calendar. Just two giants out in the dark, pulling on the Earth with a patience that makes human history look like a single afternoon. So let me show you the machine that's been deciding the fate of the ice. The machine hiding in plain sight at the edge of the solar system, and why the planet you're standing on has never really been in control of its own climate. Start with a fact that should not be true, but is. The Earth's climate, stretched across hundreds of thousands of years, is not random. It does not drift. It keeps a beat. Cold, then warm, then cold again. Glaciers grinding south across whole continents, then crawling back north, over and over, with a regularity you'd expect from a clock, not a planet. Ice sheets more than 3 kilometers thick, almost 2 miles of solid ice, have buried the land your cities sit on, melted away and buried it again. And the timing of all that freezing and thawing is not an accident. Something is keeping the rhythm. For a long time, nobody could say what. The cold ages were obvious in the rock, in the scratched and gouged landscapes left behind by ancient glaciers. But the why was a wall. What could possibly reach out and freeze half a planet on a schedule, then warm it back up, again and again, for millions of years? The answer came from a man working alone with a pencil. Milankovitch, a Serbian engineer and mathematician, spent years, including a stretch as a prisoner of war during the First World War, filling notebooks with one of the most tedious calculations anyone has ever attempted by hand. He was working out, century by century, how the shape of Earth's orbit and the tilt of its axis slowly change over tens of thousands of years. No computer, no calculator, just arithmetic, page after page, chasing the idea that the ice ages were written in the geometry of how Earth moves around the sun. He was right. And here is the part that turns a dusty piece of climate science into something that should genuinely unsettle you. Earth does not move in a fixed, reliable way. 3 things about its motion drift, slowly, on long cycles. The shape of its orbit stretches and rounds out. The tilt of its axis nods up and down by a couple of degrees. And the axis itself wobbles like a spinning top losing its balance, tracing a slow circle over about 23,000 years. Stack those 3 rhythms on top of each other and you get the pattern that drives the ice. When they line up the wrong way, the far north stops getting enough summer sunlight to melt the previous winter's snow. The snow survives the summer. It piles up. Year after year, century after century, it grows into an ice age. So the ice isn't really about temperature in the way you'd think. It's about geometry. It's about whether the northern summers are warm enough to undo the winters, and that depends entirely on how Earth is tilted and where it sits in its stretched, drifting orbit. Move the planet's geometry and you move the ice. Which raises the question that should have been bothering you for the last minute. What moves the geometry? What stretches Earth's orbit and tugs its tilt? The planet can't do it to itself. It can't. And this is where the two giants step out of the dark. The shape of Earth's orbit, that slow stretch from nearly circular to slightly oval and back, is not Earth's doing at all. It's the gravity of the other planets, pulling on us across hundreds of millions of kilometers, and the heaviest hands on Earth's orbit belong to the 2 largest planets in the solar system, Jupiter and Saturn. Let me make Jupiter's size real for a second, because the word giant gets thrown around until it means nothing. Jupiter is more than twice as massive as every other planet combined. Pour all 7 other worlds onto one side of a scale, and Jupiter still wins, easily. More than 1,300 Earths could fit inside it. When something this heavy circles the Sun, it doesn't just sit in its lane. Its gravity reaches inward across the whole solar system, and it never stops pulling on us. Saturn, the second giant, is lighter, about 95 times the mass of Earth, and much farther away. But far away does not mean harmless. Over tens of thousands of years, its steady, repeated pull adds up into a force that can reshape an orbit. Think of Earth's orbit as a loop of wire, and Jupiter and Saturn as two hands slowly bending it. One pulls it a little more oval, the other, over thousands of years, eases it back toward round. Neither hand is rushing, but they never let go, and they never tire. And the result is that Earth's orbit is constantly, gently breathing in and out of shape on a cycle that runs about 100,000 years long. That 100,000-year stretch is one of the strongest beats in the entire Ice Age record. The giants are not a footnote to Earth's climate. They are one of its authors. And don't write off Saturn as the smaller partner just because it's lighter. There's a reason it matters out of proportion to its mass. And it comes down to a kind of cosmic rhythm called resonance. Jupiter and Saturn are locked in a slow gravitational conversation, where for roughly every 5 trips Jupiter makes around the Sun, Saturn makes 2. Their closest approaches land in nearly the same places again and again, so their pulls don't cancel out into noise. They reinforce. It's the same reason a child on a swing goes higher when you push at exactly the right moment instead of randomly. Two giants, pushing in time with each other, can move things that neither could move alone. So when Saturn leans on Earth's orbit, it isn't acting as a bystander to Jupiter. It's a second author, writing in rhythm with the first. And the climate of your planet is the page they're writing on. Saturn carries its own quiet menace too, the kind that only shows up when you look closely. It is so light for its size that in theory, if you could find a bathtub big enough, the whole planet would float, less dense than water. And yet that airy, almost weightless giant still has enough reach to help tilt the balance between ice and open ground on a world it will never come near. There's something deeply strange about that. The two objects deciding part of Earth's fate are a planet you could not float a boat on and a planet that would float in a bathtub, working together across the emptiness with a patience no living thing could match. Stay with me, because the implication here is bigger than it first sounds, and it cuts close to home. The stable, mild stretch of climate that let human civilization happen, the calm window where our ancestors stopped chasing herds across the tundra and settled down to grow wheat and build the first towns, was not guaranteed. It was handed to us. We came out of the last ice age into a warm, steady period, and we built everything we have inside it. Farming, cities, writing, every empire, every invention, all of it fits inside one warm interval between glaciations. And the length and warmth of that interval is shaped, in part, by where Jupiter and Saturn have nudged our orbit. The giants set the room temperature. We just walked in and got comfortable, with no idea who was holding the thermostat. So the next time someone calls Jupiter a far-off ball of gas with nothing to do with daily life on Earth, you can hand them this. The two biggest planets in the solar system have a measurable, ongoing grip on whether your part of the world is buried under ice or open to the sky. They've had it the entire time life has existed here. They have it right now. Now, before you go outside and stare nervously at the sky, let me be honest with you. Because this is exactly the kind of fact that gets twisted into something it isn't. The orbital cycles are slow. We're talking tens of thousands of years for the rhythm to swing. On its own, this machine is not about to drop an ice age on your grandchildren. And there's a faster, closer force acting on Earth's climate right now. The carbon we're pouring into the air, working on a timescale of decades, not millennia. The giant's clock is slow. What we're doing to the atmosphere is fast. Both are real, they just run at completely different speeds. But the unsettling thing was never the speed. It's the indifference. This machine does not know we exist. It was turning long before there was anything alive to feel it, and it will keep turning long after the last trace of us is gone. The warmth that built our entire world was an arrangement of gravity we had no vote in and no power over. We are tenants in a house whose foundations shift on a schedule we can barely perceive, paying rent in time we don't even know we owe. Let me pull you out to Jupiter itself for a moment, because the planet, with its hand on our climate, is even stranger up close than it is from a distance.
Jupiter has no surface you could ever stand on. None.
Drop toward it, and you'd fall first through bands of pale ammonia clouds, then deeper into a hydrogen atmosphere that grows thicker and hotter the further down you go, until the pressure becomes so crushing that the gas around you stops behaving like gas at all. Thousands of kilometers down, several thousand miles, the hydrogen is squeezed so hard it turns into a liquid metal. An ocean of metallic hydrogen wrapping the planet's core. A sea of a substance that doesn't exist anywhere on Earth. There is no line where atmosphere ends and ground begins. There's just more and worse and heavier all the way down. And the pressure down there is almost impossible to picture, honestly. At Earth's surface, you live under one atmosphere of pressure and never feel it. Inside Jupiter, it climbs to millions of times that. Enough to flatten any machine we could build long before it reached even the halfway point. We have never touched Jupiter's core, and with the technology we have, we never will. Everything we know about the inside of this planet, we learned from the outside, from its gravity, from its magnetism, from watching how it bends the space and the spacecraft around it. Here's a fact worth keeping. Jupiter gives off more heat than it receives from the Sun. It's slowly leaking warmth left over from its own birth, energy stored up 4.5 billion years ago when it first formed and squeezed itself together under its own crushing gravity. And it's still shrinking, very gently, right now, contracting inward by a small amount every year. And that slow collapse releases heat. So Jupiter glows faintly with a memory of how it was made. It has been cooling at that cruel for the entire age of the solar system, and it still isn't finished. Hold that whole picture at once. A planet so vast it bends the orbit of a world hundreds of millions of kilometers away, leaking the warmth of its own ancient formation, with its gravity quietly helping decide when ice swallows our continents. And most people will live and die without ever knowing a single piece of it was happening above them. There's another side to Jupiter worth knowing, because it makes the slow, patient way it works on Earthland even harder by contrast.
Jupiter spins faster than any other planet in the solar system. A full day there lasts under 10 hours. Sit with that. A ball more than 11 times wider than Earth, with a mass of over 300 Earths, whirling so fast that one complete rotation takes less time than a single one of your work shifts. That speed is why Jupiter isn't a perfect sphere. It visibly bulges at its equator, squashed like a ball someone sat on, because it's spinning hard enough to fling its own middle outward into space. So the same planet does one of the fastest things in the solar system and one of the slowest at the same time. The frantic 10-hour spin you could watch in a single afternoon through a backyard telescope. Cloud bands rolling past. The grip on Earth's orbit takes 100,000 years to complete one swing. Violent and patient, all at once. And it's the patience side that moves walls of ice across continents. So how do we even know any of this, if the rhythm is too slow for any human to live through? This is where it stops being a bold story and becomes testable science, and it stands on two legs. The first is the math. Scientists build models of the entire solar system, every major body and the gravity between them. Then let those models run forward and backward across millions of years, tracing the orbits step by step. They don't put the rhythms in by hand. The long cycles emerge on their own, just from the gravity. Earth's orbital shape rises and falls in waves, with periods near 100,000 and 400,000 years. And those numbers fall right out of the pull of Jupiter and Saturn. The giant's influence isn't assumed, it appears. But a simulation alone could be wrong. So here's the second leg, and it's the one that gives me chills. The proof is written into the Earth itself. Drill down into ancient layers of seabed sediment and polar ice that piled up over millions of years, and you find the climate cycles preserved like rings in a tree. Bands of warm and cold, wet and dry, stacked one on top of another in repeating patterns. When scientists measure the spacing of those layers, the orbital rhythms are right there in the stone and the ice. The same 100,000-year beat the math predicts. The giants left their fingerprints in our mud and our glaciers, written down by the very climate they helped shape, long before anyone was alive to read it.
That's the thing that gets me every time. We did not invent these cycles. We dug them up. They were waiting in the geology, in the ice cores pulled from deep under Antarctica, in the layered cliffs of ancient seabed. A signature left by a clock running far out in the dark. The rocks remember Jupiter and Saturn, even though no single human ever could. And the record they keep goes back further than most people imagine. This isn't one ice age and one thaw. Over the last few million years, the Earth has swung in and out of glaciation dozens of times. The ice has come and gone, again and again, like a tide measured in tens of thousands of years instead of hours. Each time, sheets thick enough to crush the landscape, spread down over the northern continents, locked up so much of the world's water that sea levels dropped by more than 100 meters, over 300 feet, and exposed land bridges that early humans walked across to reach new parts of the planet. Then the orbit shifted, the northern summers warmed, the ice retreated, and the seas rose again to drown those same bridges. The map of the world you know, the coastlines, the islands, the places people first settled, was carved in part by a rhythm set in the outer solar system. Stand where I'm standing for a second and put yourself inside one of those cold ages. Around 20,000 years back, the last time the ice was at its worst. If you live anywhere across the northern half of the world, imagine the spot under your feet buried beneath a wall of ice taller than the highest skyscraper in your city. Not a glacier you'd hike to, a frozen ceiling pressing down on the land where your home is. In some places, more than 3 kilometers thick, almost 2 miles of solid ice, grinding slowly southward and scraping the ground flat as it goes. The air is bone dry and brutally cold. The sea has pulled back so far that beaches you know today would sit far inland. The shoreline retreated over the horizon. Whole forests are gone, replaced by frozen plain. And none of it was triggered by anything on Earth. The thing that decided your patch of the planet would freeze was the angle of the sunlight in the far north, set by a wobble and a stretch in Earth's orbit, nudged by 2 planets you could not even see in the daytime sky. That is what it means to say the giants keep the rhythm. It isn't an abstraction. It's a wall of ice where your street is. Milankovitch died in 1958, decades before his idea could be properly tested. For a while, plenty of scientists doubted it. Pencil and paper calculations about distant planets felt too tidy, too far removed from something as messy as global climate. The turning point came in 1976, when a team led by the scientists James Hayes, John Embry, and Nicholas Shackleton published an analysis of deep-sea sediment cores stretching back almost 500,000 years. They measured the climate rhythms buried in the seabed, and there they were, the exact periods Milankovitch's geometry predicted. The orbital tilt cycle near 41,000 years, the wobble near 23,000, the orbital stretch near 100,000. A man with a pencil had heard the heartbeat of the ice ages decades before anyone could confirm it, and the planet had been keeping that exact beat all along. The paper that proved it carried a title that said the quiet part out loud. It called these orbital cycles the pacemaker of the ice ages. But the math and the rocks only got us so far. To really understand Jupiter, we had to go there. And going there is its own quiet story of machines hurled into the dark on one-way trips. The first to arrive was Pioneer 10 in 1973, a small probe that did something nobody was sure it could survive. It flew straight through Jupiter's radiation belts, an invisible storm of charged particles trapped by the planet's enormous magnetic field, and lived just long enough to send back the first close-up photos. That magnetic field, by the way, is the largest single structure in the solar system after the Sun's own reach. If your eyes could see it from Earth, it would look bigger in the sky than the full moon, a vast, invisible bubble with whole moons orbiting inside it. Then came the 2 Voyagers in 1979, and they caught Jupiter in motion. They filmed the storm bands flowing, watched the great red spot churn, and discovered that one of Jupiter's moons, a little world called Io, was covered in active volcanoes spraying sulfur into space. Nobody expected that. A small moon should be a dead, frozen rock. Instead, Jupiter's gravity was kneading Io so hard, squeezing and releasing it on every orbit, that the friction kept its insides molten. The giant was torturing its own moon into staying alive. Even Jupiter's family doesn't get to rest. The one that committed was Galileo, which reached Jupiter in 1995 and spent years circling it, and on the way in, it dropped a probe straight into the atmosphere to taste it during the fall. That probe plunged in behind a heat shield that flared to thousands of degrees, then opened a parachute and drifted down through the clouds for 58 minutes, radioing back the first direct measurements ever taken from inside a giant planet.
Temperature, pressure, the chemistry of the air, all of it, until the rising heat and pressure finally killed the transmitter. Within hours, the probe was gone entirely, melted and vaporized somewhere in the deep atmosphere. It didn't crash, it simply stopped existing, swallowed by the planet it came to study. And right now, today, a spacecraft called Juno is looping over Jupiter's poles, its electronics sealed inside a vault of titanium to shield them from that radiation storm, peering deeper into the planet than anything before it. Juno is the reason we now know Jupiter's core isn't the neat, solid ball we expected, but something stranger, a fuzzy, smeared-out center that blurs into the layers above it. Every one of these machines was a gamble, thrown across hundreds of millions of kilometers to a planet that does not want visitors. And every one came back with the same message. Jupiter is bigger, stranger, and more powerful than the calm picture in the textbook ever let on. Let me put the scale of this in terms your own body can feel, because the numbers go numb if you don't anchor them. To live through one full swing of Earth's 100,000-year orbital cycle, you would need to be born today and keep living, awake and aware, for 100,000 years straight. The entire span of recorded human history, every war, every empire that rose and fell, every invention from the first wheel to the rocket that left Earth, fits inside that single swing several times over, with room to spare. You and everyone you will ever know are living through one thin sliver of one turn of a wheel the giants started spinning before our species existed. And here's the part that makes it personal. We happen to be alive in the warm interval, the open window between glaciations, not because we earned it or chose it, but because of where the wheel happens to sit right now. Almost everyone who ever lived was born somewhere on that slow turn and felt nothing change. Because on a human timescale, nothing visibly does. We got the calm stretch, we got the thaw. Pure timing handed us a stable sky to build under. That isn't destiny, it's luck. But it's the kind of luck worth stopping to feel. There's one more layer, and it's the one that makes Jupiter feel less like a planet and more like a slow, immense force you should genuinely respect. Its grip doesn't stop at gently shaping our orbit. Over deep time, the gravitational tug-of-war between Jupiter and the inner planets can build up in ways that turn dangerous. Run the solar system forward far enough in those same simulations, billions of years out, and the orbits stop being perfectly predictable. Tiny nudges accumulate, then feed on themselves. In some of these long-range models, Mercury, the smallest planet, the one closest to the Sun, has its orbit stretched by a slow resonance with Jupiter until, in a small fraction of simulated futures, it destabilizes completely. Flung onto a path that could end in a collision with Venus or with the Sun, or in the worst cases, thrown into the inner solar system entirely. Let me be careful here, because this is the kind of fact that gets ripped out of context. The odds are low, somewhere around 1% over the next 5 billion years, and that timeline runs out past the point where the Sun itself begins to die. This is not a warning about anyone's lifetime, but it tells you exactly what kind of object Jupiter is. It is not a neighbor. It is a slow, colossal engine of gravity that has been quietly steering the fates of the other planets since before Earth had oceans. And it will keep steering them long after the Sun begins to fail. Its hand on our ice ages is only the part of that power gentle enough to let us survive underneath it. Picture Jupiter up close one more time, even though it would kill you 100 different ways. You couldn't stand on it, there's nothing to stand on, but float in the upper clouds, and the thing that would overwhelm you isn't the cold or the pressure. It's the speed and the scale together. Storms wider than entire planets rolling beneath you. The Great Red Spot alone,
that famous swirling vortex, has been raging for centuries and is wide enough to swallow the Earth whole. A single storm that has outlived every person who ever pointed a telescope at it. Winds in the cloud bands tear along at hundreds of kilometers an hour, hundreds of miles an hour, faster than any storm Earth has ever produced. And the whole vast machine spins through a full day before you'd finish one night's sleep. And underneath all that noise, the silence. The slow, patient pull on a small blue world hundreds of millions of kilometers away. Indifferent to the storms on Jupiter's surface, indifferent to the ice it shapes on ours. That's the thing about Jupiter that's hard to shake once you see it. The loud part, the spin, the storms, the red eye staring out of the clouds, isn't even the important part. The important part is the quiet force you can't see at all, the one that's been with us the whole time. One last way to feel the distance. Light is the fastest thing there is, moving at about 300,000 kilometers a second, roughly 186,000 miles a second. Even at that impossible speed, sunlight takes more than 40 minutes to reach Jupiter, sitting out there, on average, around 778 million kilometers from the Sun, nearly 484 million miles. And yet, across all that emptiness, Jupiter's gravity still reaches inward, all the way to us, and helps decide whether the north freezes. Gravity does not fade with distance the way our instincts insist it should. It crosses the dark patiently, and it never lets go. So pull all the way back and look at what we've actually uncovered. Two planets, far out in the cold, with their hands on the shape of Earth's orbit. A rhythm of ice and thaw they help keep, written into the rock and the glaciers of a world they will never touch. A warm window between glaciations that we happened to be born into, and built our entire civilization inside. And a slow machine of gravity that started turning before our species existed, and will keep turning long after we're gone, completely unaware that anything down here ever learned its name. The giants aren't doing anything violent in this exact moment. No impact, no explosion, no storm you could film. They're doing something quieter and far heavier than any of that. They're keeping time. And the only reason that time isn't passing in total silence and total darkness, unwitnessed, is that one curious species on one small rock learned to read the clock written across the sky and buried in the ground beneath its feet. We are incredibly small. We live inside the slow breath of planets that have no idea we're here, that wouldn't notice if we vanished, that will go on shaping the Earth's orbit for billions of years after the last of us is gone. But we figured out the rhythm anyway. We pulled it out of simulations and ice cores and layered cliffs, and we understood, for the first time in the history of life on this planet, just how much of our warm, fragile, improbable story has always depended on giants we will never touch and never fully understand. That's the part worth carrying with you tonight, after the screen goes dark. Not fear, not doom. Just the strange, quiet weight of knowing that the stable sky that let your ancestors stop running and start building was handed to you by the slow turning of orbits shaped by worlds you'll never see, and that you were lucky enough to be born in the warm, open window before the ice comes back. Jupiter and Saturn have been keeping time since long before we had a word for it. Tonight, just for a moment, we got to watch the clock. Thanks for watching, and I'll see you in the next one.